Right now, a moon bigger than the planet Mercury is sitting inside our solar system. It has oceans, it has rain, it has weather, and until 2 years ago, we had never seen its surface clearly. Titan, Saturn's largest moon, wrapped in a haze so thick it blocked every telescope we ever aimed at it. Then James Webb changed everything. We are going to scan Titan from top to bottom. Methane seas, ice volcanoes, a buried ocean that might hold something alive, rain that falls like snow, dunes made of plastic. If you enjoy the journey, subscribe and leave a like. It genuinely helps. 33 chapters. One moon that rewrites what we thought we knew about life. Let's begin. Picture the most alien place you can imagine. Oceans the color of tar, rain that drifts down like feathers, skies the color of a dirty orange, ground made of solid ice, hard as concrete, and a moon so big it swallowed the planet Mercury in size. That moon is Titan, and it orbits Saturn about 886 million miles from the Sun. Titan is Saturn's largest moon and the second largest moon in the entire solar system. Only Jupiter's moon Ganymede beats it. Titan stretches nearly 3,200 miles across. To put that in your head, that is roughly the distance from Los Angeles to New York and back again. For a long time, astronomers had no idea what was hiding under its surface. Every time they pointed a telescope at Titan, they saw the same thing: a featureless orange ball, no craters, no mountains, no surface detail at all, just a thick, murky sphere that refused to give anything away. The problem was the atmosphere. Titan is the only moon in our solar system with a dense, thick atmosphere. It is not a thin layer of gas clinging to a rock. It is a full, heavy blanket of nitrogen and methane that reaches nearly 370 miles up into space. Earth's atmosphere only reaches about 60 miles before it fades. Titan's goes 6 times higher. That atmosphere is packed with organic compounds, tiny carbon-based particles that cluster together and form a permanent orange smog. Think of the worst smog day in Los Angeles, then multiply it by 10,000, then wrap it around an entire world. That is what Titan looks like from space. The smog blocks visible light completely. Any regular telescope looking at Titan in ordinary light sees nothing but the haze. So for 300 years, from the moment Dutch astronomer Christiaan Huygens discovered Titan in 1655, astronomers knew it existed but could not figure out what was happening on the ground beneath that orange veil. Huygens spotted the moon using a handmade telescope. He noticed a bright point near Saturn that moved along with the planet. He tracked it for weeks, confirmed it was orbiting Saturn, and recorded the discovery. He had no idea he had found one of the most complicated worlds in the solar system. Hundreds of years passed. Telescopes got bigger. Technology improved. Spacecraft were launched. Pioneer 11 flew past Saturn in 1979. The Voyager probes flew past in the early 1980s. Every single one of them looked at Titan and saw the same orange blur. Voyager 1 got close enough to confirm the atmosphere was real and thicker than Earth's. It measured the surface temperature at around -290 degrees Fahrenheit, cold enough to freeze water solid as granite, cold enough that the only liquid on the surface would have to be something other than water. Scientists started to suspect something wild was happening under that haze. The chemistry suggested methane, lots of it, maybe rivers, maybe lakes, maybe entire oceans of liquid methane sitting on the surface of a moon 1 billion miles away. But suspecting something and seeing it are two completely different things. The orange haze held its secrets for decades after Voyager. Every attempt to image the surface directly failed. The smog won every time. Something bigger would need to come along, something that did not play by the rules of ordinary light, and it was already being built. The haze on Titan is alive. Not literally alive, but constantly growing, constantly churning, and constantly being replaced. It is one of the most active chemical systems in the entire solar system, and it has been hiding a world from us for billions of years. Here is how it works. Titan's atmosphere is mostly nitrogen. The the same gas that makes up about 78% of Earth's air. But mixed into that nitrogen is methane. And when sunlight hits methane high in the atmosphere, it breaks it apart. The fragments do not just float away, they recombine. They stick together and form bigger, heavier molecules. These new molecules are organic compounds, meaning they are built around carbon atoms, the same type of chemistry that makes up living things on Earth. These heavy molecules sink slowly through the atmosphere. As they drift down, they clump together into tiny particles, each one smaller than a grain of fine dust. Billions of these particles swarm together and form layers of orange haze, one layer sitting on top of another, stacked all the way up through the atmosphere. Titan's haze is not like fog on Earth that burns off in the morning sun. This haze is permanent. It regenerates faster than it can be cleared. Sunlight keeps breaking methane apart, and the atmosphere keeps producing more particles to replace any that fall to the ground. From space, this makes Titan look like a smooth, featureless orange marble. Every detail of the surface below is completely invisible to any camera or telescope working in normal visible light. This frustrated scientists for decades. They could measure the atmosphere's chemistry from a distance. They could detect signals of nitrogen and methane. But seeing the actual ground, mapping the terrain, watching weather systems form and move, was completely out of reach. The Cassini spacecraft changed part of this when it arrived at Saturn in 2004. Cassini carried a special radar instrument. Radar works by sending out radio waves that bounce off surfaces and return to the receiver. Radio waves cut through the haze the way visible light cannot. The radar on Cassini began mapping Titan's surface by bouncing signals through the atmosphere and reading what came back. Those radar maps revealed something stunning. Titan had coastlines. It had river channels carved into the ground. It had long, narrow dunes spreading across its equator. And near the North Pole, it had huge dark patches that looked exactly like lakes and seas. The maps confirmed what scientists suspected. Titan had liquid on its surface, liquid methane, entire bodies of it. But radar maps are rough. They show shapes and outlines. They tell you something is there without showing you what it actually looks like. Scientists wanted real images. They wanted to see the colors, the textures, the clouds, the weather happening in real time. Visible light was blocked. Radar gave only outlines. Something new was needed. The answer was infrared light. Infrared sits just beyond the range of human vision, in the part of the spectrum we feel as heat. Certain wavelengths of infrared light can cut through Titan's haze the way a flashlight cuts through fog, partially at least. Some of these wavelengths squeeze through narrow gaps in the atmospheric chemistry where the organic particles do not absorb them. Scientists had used ground-based infrared telescopes to catch glimpses of Titan's surface through these gaps, but the images were blurry and limited. The gaps were narrow, and the light that came through was faint. What they needed was an infrared telescope powerful enough to detect the faintest signal coming through those tiny windows in the haze. What they needed was something parked far above Earth's own atmosphere, looking outward with instruments more sensitive than anything that had existed before. That telescope was already up there, and its first look at Titan was about to crack the mystery wide open. Most people think of light as one thing. You flip a switch, the room gets bright, done. But light is actually a huge family of different waves, and the ones your eyes detect are only a tiny slice of what exists. Think of it like sound. You can hear certain pitches. A dog whistle is too high for you to hear, but a dog catches it instantly. Light works the same way. Your eyes are tuned to a specific range. Below that range is infrared. Above it is ultraviolet. Your eyes simply cannot detect them. Infrared light carries heat. You feel it every time you stand near a fire or step into sunlight. Your skin detects infrared, even though your eyes cannot see it. Every warm object in the universe radiates infrared light. Your body is doing it right now. Here is where it gets important for Titan. Different materials absorb different types of light. Titan's orange haze particles are very good at absorbing visible light, which is why regular telescopes see nothing but smog. But those same particles are much less effective at absorbing certain infrared wavelengths. Some infrared waves slide straight through the haze like they barely notice it. Scientists call these narrow windows in the atmosphere where infrared slips through the spectral windows. Titan has several of them at specific infrared wavelengths. If you aim an infrared detector tuned to exactly those wavelengths at Titan, the haze becomes semi-transparent. You do not get a perfectly clear view, but you get something: shapes, brightness differences, surface features emerging from beneath the smog. Ground-based infrared telescopes on Earth have been using these windows for years, but Earth's own atmosphere gets in the way. Water vapor and other gases in our air absorb some of the same infrared wavelengths that pass through Titan's haze. So even when infrared light comes all the way through Titan's atmosphere, it still has to fight through our atmosphere to reach the telescope. The signal gets muddied. To truly exploit those spectral windows, you need a telescope that lives in space, above Earth's atmosphere entirely. That is one of the core reasons the James Webb Space Telescope is so powerful. It orbits about 1 million miles from Earth, far beyond our atmosphere. It carries instruments built specifically to detect infrared light with precision that no ground-based telescope can match. Its primary mirror is nearly 21 feet wide, made of 18 gold-coated hexagonal segments. Gold reflects infrared light exceptionally well. Webb's near-infrared camera, called NIRCam, can detect infrared at exactly the wavelengths that slip through Titan's haze. Its near-infrared spectrograph, called NIRSpec, can take that incoming light and spread it into a spectrum, measuring exactly which chemical signatures are present at each wavelength. Together, these instruments do not just pierce Titan's haze, they read it. They measure what the haze is made of, how thick it is at different altitudes, and what the surface below is doing. When astronomers decided to point Webb at Titan, they were not just hoping for clearer pictures. They were deploying the most advanced infrared observatory ever launched directly at a target that had been protecting its secrets for centuries. The question was no longer whether Webb could see through the haze. The question was, what would be waiting on the other side? It was early November 2022. The James Webb Space Telescope had only been delivering science images for a few months. It had already photographed the deepest galaxies ever seen. It had stared into the atmospheres of distant planets orbiting other stars. Scientists were still learning what the telescope was truly capable of. Then came the Titan observation. On November 4th, 2022, Webb's instruments locked onto Saturn's largest moon. The telescope pointed its near-infrared camera at Titan from about 886 million miles away and began collecting light. Think about what that means. Webb was gathering photons, individual packets of light that had traveled nearly 1 billion miles, punched through hundreds of miles of Titan's orange smog, slipped through one of those narrow infrared windows in the atmosphere, crossed the rest of the distance to the telescope, and landed on a detector the size of a small notebook. And from that faint signal, scientists were going to reconstruct what the surface of another world looked like. The images came back. The team processed the data, and what appeared on their screens stopped them cold. The images showed Titan clearly. The surface features were visible. You could see the brightness differences between the dark hydrocarbon seas and the bright icy highlands. The familiar outlines from Cassini's old radar maps were suddenly filled in with texture and contrast. For the first time, scientists were looking at Titan's surface and atmosphere together in a single real image, not a radar outline. But what grabbed everyone's attention immediately was not the surface. It was two bright spots sitting above it, clouds. Two enormous methane clouds, glowing brightly in the infrared images. One of them was positioned over the northern polar region, directly above Kraken Mare, the largest known liquid sea on the moon. The second cloud appeared near the equator. These were active weather systems, visible and confirmed in real time. The team knew immediately that this was significant. Titan's climate is driven by seasons, just like Earth's, except each season on Titan lasts about 7 Earth years. The Northern Hemisphere was coming out of its summer in late 2022. Models had predicted that this would be prime time for cloud formation in the north. The Webb images confirmed those models with stunning clarity. One of the lead scientists on the Titan observation team described the images as simply extraordinary. The clarity was beyond what they had expected for the first attempt. There was one problem, though. Webb is a busy telescope. It cannot sit and stare at a single target for days on end. Other scientists around the world had booked time on Webb for their own research. The telescope had to move on. That meant the team had a narrow window. The clouds they had just discovered were active. Weather systems change. If no one watched Titan for the next few days, they might lose the chance to track how those clouds evolved. So they made a call, not to another space telescope, to a mountain in Hawaii. The images from Webb's near-infrared camera were different from anything that had come before, not sharper versions of old pictures. Genuinely new information that changed the map. Previous infrared observations of Titan, taken from ground-based telescopes, had given scientists a rough idea of the surface. They could identify that the northern region was darker, likely covered in liquid. They could see that the equatorial region was brighter, probably drier, but the details were blurry. The resolution was low. Major surface features bled into each other. Webb changed the resolution completely. The near-infrared camera captured Titan through several specific infrared filters simultaneously. Each filter corresponds to a different wavelength that passes through the haze to a different depth. Some filters reveal the upper atmosphere, others cut deeper and show the lower atmosphere. The deepest filters reach all the way to the surface itself. By stacking these layers, the team built a detailed picture of Titan from the top of the haze down to the ground. What came out was a map with real contrast and real structure. The dark northern regions resolved into the clear outlines of the hydrocarbon seas. Kraken Mare, sitting in the North Polar Zone, appeared as a deep, dark patch. It is the largest of Titan's seas, larger than the Caspian Sea on Earth, and it reaches depths of nearly 1,000 feet. The Webb image showed its coastline with a definition Cassini's radar had only hinted at. Nearby, another sea called Ligeia Mare appeared as a separate dark region, smaller than Kraken, still enormous, still filled with liquid methane and ethane at negative 290 degrees Fahrenheit. Moving toward the equator, the surface brightened. This is where Titan's great dune fields stretch across the landscape. These dunes are nothing like the sand dunes in the Sahara. They are made of complex organic molecules, hydrocarbon particles that fall from the smog layer above and accumulate on the surface over millions of years. The dune region, called Bellet, showed up clearly in the Webb images as a wide, bright band circling the moon's midsection. Even more striking was the bright region called Adiri, sitting near the equator. Scientists believe this is elevated terrain built from water ice bedrock. On Titan, water ice acts like rock because the temperature is so far below freezing that ice becomes as hard and durable as granite. Adiri showed up brightly in the infrared because the ice reflects infrared light differently than the dark organic material covering the rest of the surface. None of this is theory. These features had been identified before by Cassini's radar, but seeing them in an actual image, in light that left Titan's surface and traveled through space to land on Webb's detector, was a completely different experience. It was the difference between a blueprint of a building and a photograph of it. And this was just the surface. The atmosphere above it was even more interesting. The same images that showed the ground also showed cloud structures and haze layers sitting at different altitudes above Titan. The separation between the surface and the atmospheric layers was clear enough to analyze independently. Titan had revealed its face. After centuries of hiding behind orange haze, the world below was visible, but the clouds sitting above that surface carried a message of their own. The clouds were the first thing that jumped out. In the Webb images from November 4th, 2022, two bright white structures stood out clearly against the rest of the atmosphere. They were not background haze. They were distinct cloud formations, dense enough to reflect infrared light strongly enough to dominate the image at those altitudes. The larger of the two clouds sat over Titan's north polar region, directly above Kraken Mare. The second cloud appeared farther south, hovering near the equatorial zone. On Earth, clouds form when water evaporates from the surface, rises into the atmosphere, cools, and condenses back into liquid droplets or ice crystals. The process on Titan works the same way, just with a different substance. Instead of water, it is methane. Methane evaporates from the liquid seas on Titan's surface. It rises through the lower atmosphere. As it gains altitude, it cools further and condenses into cloud droplets. These droplets cluster together and form the bright, fluffy structures that Webb captured. The position of the northern polar cloud was exactly where climate scientists expected it to be. Titan's seasons are driven by the tilt of Saturn's axis, as Saturn orbits the Sunday. The northern hemisphere had been experiencing its summer during the years leading up to the Webb observation. Warmer periods in summer increase the rate of methane evaporation from the seas below, feeding the cloud formation process. The polar region above Kraken Mare was the predicted hot zone for cloud activity during this part of the seasonal cycle. Seeing the cloud exactly where the models predicted was a significant result. It meant the climate models built to describe Titan's weather were working correctly. Scientists had spent years building those models using data from Cassini and from ground-based observations. Webb's images provided the clearest direct confirmation yet that those models captured something real about how Titan's atmosphere operates. The equatorial cloud was slightly more surprising. Equatorial cloud activity on Titan had been observed before by Cassini, but it was considered less common than polar cloud formation. Seeing both a polar cloud and an equatorial cloud active at the same time suggested a more energetic and widespread weather event than scientists had expected for this point in the seasonal cycle. The two clouds together painted a picture of a moon in the middle of an active weather system stretching across thousands of miles simultaneously. There was also something else embedded in the data. The near-infrared camera images showed faint streaks of brightness connecting some regions. These might be thinner cloud structures or trails of methane mist drifting in Titan's winds. The exact nature of these faint features was not immediately clear, but they pointed to atmospheric circulation patterns spreading across the moon far beyond the two main cloud peaks. Titan's atmosphere was moving, churning, transporting material across vast distances, but a single snapshot only tells part of the story. To understand what these clouds were doing, scientists needed to watch them change over time. They needed to see whether the clouds were growing, shrinking, moving, or breaking apart. Webb had already moved on to its next target. The clock was ticking. What happened next would require a completely different kind of telescope. Finding clouds might sound simple. Clouds are everywhere on Earth. But on Titan, detecting active cloud formations was a confirmation of something much bigger than just seeing some fluffy white shapes. It was proof that Titan has a full, working atmospheric engine. Weather on Earth is driven by one substance. Water moves through a complete cycle, evaporating from oceans and lakes, rising as vapor, cooling into clouds, falling as rain, collecting in rivers, and flowing back into the sea. That complete loop powers hurricanes, thunderstorms, seasonal rain patterns, and the global movement of heat around the planet. For that kind of cycle to work, a world needs four things. It needs a liquid substance on its surface. It needs that substance to evaporate and rise. It needs the atmosphere to be cold enough at altitude to condense the vapor back into droplets. And it needs gravity to pull the droplets back down as rain. Titan has all four. The liquid is methane. The atmosphere is cold enough throughout because temperatures are always far below freezing. Gravity holds everything together, though it is weaker than Earth's, just strong enough to pull methane rain down slowly. Scientists had suspected for years that Titan's methane cycle was real. The surface had rivers. Those rivers had to be carved by something flowing over a very long time. The presence of active clouds in the Webb images was the clearest evidence yet that the cycle was not just a historical process left over from the ancient past. It was happening right now. The location of the clouds added even more weight to this conclusion. The polar cloud sitting above Kraken Mare did not appear at random. Kraken Mare is the largest liquid body on Titan. It contains more liquid than all of Earth's Great Lakes combined. A sea that size produces enormous amounts of methane evaporation, especially during the northern summer when the surface receives slightly more sunlight. The cloud forming directly above it was the visible result of that evaporation happening in real time. The equatorial cloud added a different layer. Equatorial regions on Titan tend to be drier, covered in those vast sand dunes rather than liquid seas. Cloud formation near the equator likely means that methane from the northern seas was being transported southward through atmospheric circulation, carried by winds moving across the moon's surface. This pointed to large-scale weather patterns operating across Titan's entire globe at once. Active weather also meant something about the surface. A working methane cycle requires ongoing replenishment. Rain falls, rivers form, and liquid collects in basins. If clouds were forming and likely dropping methane rain somewhere on the surface, then Titan's rivers and seas were being actively fed and refreshed, not slowly evaporating into an empty, dry world. This made Titan feel less like a dead, frozen rock and more like a place with a heartbeat. A slow heartbeat, measured in 7-year seasons, but a heartbeat nonetheless. And somewhere beneath those active clouds, methane rain was almost certainly falling through skies, the color of rust, drifting down so slowly it would look nothing like rain at all. The next question was how fast those clouds were actually moving, and whether they were growing or dying. Someone was already working on an answer. Webb had moved on. The telescope had obligations. Dozens of other science teams around the world had booked observation time, and the schedule was tight. Titan's clouds had been photographed on November 4th. The next day, Webb was already pointed at something completely different. But the cloud images were so striking that the Titan science team knew they could not just wait until the next scheduled Webb observation. Clouds change. They grow, shift, and dissipate. A cloud system visible on one day might be completely gone a week later, replaced by clear skies or a totally different pattern. To understand what they had seen, they needed follow-up images as soon as possible. They turned to the W.M. Keck Observatory, sitting near the summit of Mauna Kea on the Big Island of Hawaii. Mauna Kea stands nearly 14,000 feet above sea level, above most of the water vapor in Earth's atmosphere that interferes with infrared observations. The Keck telescopes are among the most powerful ground-based instruments in the world. The team requested time on Keck and received approval 2 days after the Webb observation. On November 6, 2022, the Keck telescope began imaging Titan. Keck used a system called adaptive optics to sharpen its images. Earth's atmosphere constantly shifts and blurs incoming light, the same effect that makes stars twinkle. Adaptive optics works by measuring that atmospheric distortion in real time and then rapidly adjusting the shape of the telescope's secondary mirror to cancel the blur out. The mirror flexes hundreds of times per second, compensating for the air movement above the telescope. The result is images nearly as sharp as those taken from space. With adaptive optics running, Keck aimed at Titan and began collecting infrared images. What came back confirmed that the clouds were still there. Both of them, the northern polar cloud and the equatorial cloud, had survived the 2-day gap since the Webb observation. They had not dissipated or vanished overnight, but they had changed. The clouds had shifted positions. The large polar cloud had moved slightly. Its shape had changed too. What looked like a single dense mass in the Webb images had reorganized into a structure with different density regions. Parts of it had thickened, other parts had spread outward. This told scientists something critical. These clouds were active and dynamic. They were behaving like real weather systems, not static features frozen in place by Titan's slow pace. Within 48 hours, the cloud formations had already gone through visible changes. Combining the Webb and Keck observations gave the team something truly valuable. a time series. Two snapshots of the same weather event taken 48 hours apart, using different instruments, from different distances, showing consistent features that had clearly evolved. This kind of multi-observatory collaboration would become a model for how to study planetary atmospheres in the future. Webb provides the initial high-sensitivity image. Ground-based telescopes with flexible scheduling fill in the timeline. Together, they build a movie of planetary weather from 1 billion miles away. And what that movie was starting to show was a moon with weather more dynamic than anyone had dared predict. The full picture of what Keck found would raise even more questions. 48 hours. That was the gap between the Webb images and the Keck follow-up. In Earth terms, that is 2 days. In Titan terms, given that each full season lasts 7 Earth years, 2 days is almost nothing, a fraction of a single season. And yet, in those 48 hours, Titan's weather had visibly changed. The clouds had moved. Their shapes had shifted. The northern polar cloud, sitting above Kraken Mare, had reorganized into a different structure. The dense central mass had spread outward in some directions while thickening in others. Parts of the cloud that appeared compact and bright in the Webb images had softened and stretched in the Keck images. The equatorial cloud showed movement too. Its position relative to surface features had shifted, meaning it had been carried by winds blowing across Titan's lower atmosphere during the 2-day window. This rate of change was significant and somewhat surprising. Titan is a slow world in many ways. Its seasons last 7 years. Its day, the time it takes to complete one rotation, lasts about 16 Earth days. Scientists had expected its weather to match that slow pace, with changes happening over weeks or months, not hours. But the data said otherwise. The rapid cloud evolution suggested that Titan's lower atmosphere is more turbulent and energetic than previously assumed. Convective processes, where warmer gas rises and cooler gas sinks, appear to be driving fast cloud development above the surface. The methane evaporating from Kraken Mare was feeding energy into the cloud system rapidly enough to reshape the formations in less than 2 days. Think of a thunderstorm building on a summer afternoon. You can watch a thunderhead go from a small puff to a towering column in under an hour. Titan's clouds were showing a similar kind of rapid vertical development, just driven by methane chemistry instead of water. This matters for future missions in a practical way. If Titan's weather can shift dramatically in 48 hours, then any spacecraft operating in its atmosphere needs to be designed for variable conditions. A drone flying through stable, predictable air is a very different engineering challenge from a drone flying through a world where cloud systems surge and reorganize overnight. The Keck follow-up also hinted at something else. The fact that both clouds persisted across the full 48-hour gap suggested they were not brief, fragile structures. They were sustained by ongoing evaporation from the surface. The energy source feeding them was still active 2 days after Webb first spotted them. Somewhere below those clouds, methane was evaporating from the surface of Kraken Mare and feeding the system continuously. And if methane was evaporating and rising and forming clouds, the next logical step in the cycle was rain, methane rain, falling from those clouds, drifting down through the orange skies and landing somewhere on the surface of Titan. What that rainfall actually looked like from the ground was something no camera had ever captured from orbit. But understanding the rain meant first understanding the cycle that produced it. Water runs Earth. It evaporates from the oceans, rises as vapor, forms clouds, falls as rain, carves rivers, fills lakes, and flows back to the sea. That cycle has been running for billions of years. It shaped every continent, carved every canyon, and made life possible. Titan has the same cycle. The substance is different, the temperatures are different, but the structure is almost identical. Methane does on Titan exactly what water does on Earth. Start at the surface. Titan's northern hemisphere is dotted with lakes and seas of liquid methane mixed with ethane. These bodies of liquid sit exposed to the moon's thin atmosphere. Even at temperatures of -290 degrees Fahrenheit, methane still evaporates from the surface and rises into the atmosphere as vapor. As the methane vapor rises, it cools further and eventually reaches the altitude where it condenses back into liquid droplets. Those droplets cluster together and form clouds, the same bright structures Webb photographed above Kraken Mare in November 2022. The clouds grow denser as more vapor feeds them from below. Eventually, the droplets become heavy enough that gravity pulls them downward. They fall as rain. Methane rain on Titan does not fall fast. Titan's gravity is only about 1/7 of Earth's gravity. The atmosphere is thicker than Earth's, which creates more drag on falling droplets. The result is that methane rain falls extremely slowly, drifting toward the ground at a fraction of the speed of rain on Earth. It would look more like snow falling through still air than a rainstorm. When the rain reaches the ground, it flows across the surface and carves channels in the ice bedrock. Those channels connect into river systems. The rivers flow downhill and drain into the low-lying basins where the seas and lakes collect. The cycle closes. This is not a theory built purely from models. Scientists have direct evidence for each step. The seas and lakes in the north are confirmed by Cassini radar and Webb images. The clouds are confirmed by multiple observations. The river channels carved into Titan's ice surface were mapped by Cassini, and the spectral data from Webb confirmed active methane chemistry in the lower atmosphere, consistent with an ongoing evaporation and condensation cycle. The most striking parallel with Earth's water cycle is the scale. Earth's oceans cover most of the planet and drive a global weather system. Titan's methane seas are concentrated in the northern hemisphere, covering a much smaller fraction of the surface. This means Titan's methane cycle is more regional than Earth's global water cycle. Weather patterns are more intense near the northern seas and much drier near the equatorial dune fields. The seasons shift where the cycle is most active. During northern summer, the North Pole warms slightly and evaporation rates increase. The clouds build up in the north. During northern winter, the activity shifts toward the south. One full cycle of Titan's seasons takes about 29 Earth years, the same time Saturn takes to orbit the Sunday. Through one complete Saturnian year, Titan breathes methane in and out like a living world. But there is one problem with this cycle that scientists have been staring at for decades and still cannot fully explain. The methane should have run out by now. Imagine a sea bigger than the Caspian Sea, dark as motor oil, cold enough to freeze a human solid in seconds, filled not with water but with liquid methane and ethane, sitting under skies the color of a rusted iron pipe, 500 million miles from the nearest sun. That is Kraken Mare. Kraken Mare is the largest known body of liquid in the outer solar system. It stretches across the northern polar region of Titan, covering an area larger than the Caspian Sea on Earth. It reaches depths of nearly 1,000 feet at its deepest points, roughly the height of the Chrysler Building in New York. The name comes from the legendary sea monster of Norse mythology. Scientists who named it were clearly paying attention to what they were looking at. Cassini's radar first mapped the outline of Kraken Mare during its years orbiting Saturn. The radar returns showed a large, smooth, dark region in the north, exactly the kind of signal you would expect from a calm liquid surface. Radar waves bounce differently off liquids than off solid ground, and the return from Kraken Mare matched liquid almost perfectly. Webb's infrared images showed Kraken Mare as a dark patch against the brighter surrounding terrain. The sea absorbs infrared light more strongly than the ice bedrock around it, making it appear distinctly dark in the images. Its outlines match the Cassini radar maps, but with more detail visible in the surrounding coastal regions. What fills Kraken Mare is a mixture dominated by methane and ethane. At Titan's surface temperature, both of these substances are liquid. Ethane is a heavier molecule than methane and tends to accumulate in the seas as methane evaporates more readily. Some estimates suggest the ratio inside Kraken Mare might be roughly 70% ethane to 30% methane, but the exact composition remains uncertain because no probe has directly sampled the sea. The depth creates an interesting situation. Below about 300 feet, the pressure at the bottom of Kraken Mare is high enough that ethane and methane might behave differently than they do near the surface. Some researchers have proposed that at extreme depths, the liquid mixture could transition into a different phase, with strange properties unlike anything familiar. Nobody knows for certain what the bottom of Kraken Mare looks like. It could be a flat, sediment-covered plain of organic material. It could be a jagged landscape of ice bedrock carved by ancient currents. It might have features nobody has thought to predict yet. One thing is known: the waves on Kraken Mare are tiny, remarkably, almost eerily tiny. The surface of the sea sits almost perfectly flat, with waves rarely exceeding half an inch in height. On Earth, a sea of that size would be churned by winds into rolling swells of many feet. On Titan, the thick atmosphere creates less surface wind shear, and the liquid's properties damp wave formation almost completely. Standing at the edge of Kraken Mare, if a human could somehow survive the temperature, they would be looking at the calmest, darkest, deepest sea in the solar system. And somewhere beneath that glassy surface, the floor of Kraken Mare has never been touched. Something even stranger lurks in what lies beneath the entire moon, a sea the size of the Caspian Sea, and its waves are smaller than the width of your thumb. That detail stops most people cold when they first hear it, and it should, because on Earth, any open body of water that large would be heaving with swells, whitecaps, and spray. Titan's seas sit still. The reason involves physics at every level of the moon's environment. Start with wind. Waves on any ocean are generated by wind dragging across the surface. The faster the wind, the harder it pushes against the water, and the bigger the waves become. On Earth, surface winds over large bodies of water regularly reach speeds between 10 and 30 miles per hour, easily enough to build significant wave heights. On Titan, winds near the surface are much slower than on Earth. The thick atmosphere creates high atmospheric pressure at the surface, about 50% greater than Earth's sea level pressure. High pressure tends to suppress strong wind gradients near the surface. The air moves sluggishly at low altitudes. Without strong surface winds, there is little force available to push against the liquid and build waves. The second factor is the liquid itself. Water has a certain density and surface tension that responds to wind energy in a familiar way. The methane and ethane mixture in Titan seas has different physical properties. It is less dense than water and has a lower viscosity in some ways. But the combination of these properties means wave energy dissipates quickly. Any small ripple that forms tends to flatten out rapidly rather than growing into larger swells. The third factor is gravity. Titan's gravity is about 1/7 of Earth's. Lower gravity means the atmosphere above the sea sits under lower gravitational force, which affects how air masses move and interact with the surface. The combination of low gravity and thick atmosphere creates a very different relationship between the air and the liquid than anything on Earth. Scientists at Johns Hopkins University ran detailed models of wave generation on Titan's seas. Their results predicted that even under the most favorable wind conditions on Titan, waves in Kraken Mare would almost never exceed about half an inch in height. Some models suggested that for most of the year, the surface of the sea would be essentially flat to within a fraction of a millimeter. Cassini's radar data backed this up. When the spacecraft bounced radar pulses off Titan's seas, the returns were almost mirror-smooth, consistent with a flat liquid surface. Radar can detect surface roughness down to very small scales, and the seas showed almost none. The smoothness matters for future exploration. A spacecraft or probe attempting to land on or sample Kraken Mare would not face the kind of turbulence that would threaten operations on Earth's oceans. The surface would be extraordinarily calm. But calm does not mean simple. Below that glassy surface, the chemistry of the sea is complex, evolving, and largely unmapped. And above the sea, the moon's surface tells a completely different story, one written in dark, organic sand, blown by seasonal winds across thousands of miles of frozen desert. Cross the shoreline of Kraken Mare, travel south toward the equator, and the landscape changes completely. The dark seas disappear, the icy highlands flatten, And stretching across the middle of Titan, wrapping almost entirely around the moon, are sand dunes unlike anything on Earth. The region called Belet covers a massive band of Titan's equatorial zone. It showed up in Webb's infrared images as a wide, darker stripe running across the moon's midsection. Cassini's radar had already mapped it extensively, revealing long, parallel dune ridges stretching hundreds of miles, each one taller than most buildings you pass in a city. Each dune ridge on Titan runs roughly in an east-west direction, shaped by the slow seasonal winds that sweep across the equatorial region. The ridges can rise over 300 feet tall and extend for hundreds of miles without breaking. From above, Belet looks like a massive herringbone pattern pressed into the face of the moon. But what makes these dunes strange is what they are made of. On Earth, desert dunes are built from silicate sand, ground-up rock, worn down by billions of years of erosion. On Titan, there is no silicate sand blowing across the surface. The material that builds the dunes falls from the sky. Remember the orange haze. Sunlight constantly breaks methane apart in the upper atmosphere, and the resulting organic fragments recombine into larger and heavier molecules. These heavy organic compounds eventually grow massive enough to sink through the atmosphere and fall to the surface. They are sometimes described as plastic-like because they are long-chain carbon molecules, similar in basic structure to some synthetic polymers, though far more complex and varied. These particles accumulate on the ground over millions of years. Winds pick them up and move them. Because the particles are loose and light, they blow easily in Titan's slow surface winds. They drift, accumulate in topographic low points, and over time build up into the massive dune ridges seen in Belet. The color of the sand is dark brown or black. This dark coloring is part of why the equatorial band shows up differently than the bright icy highlands in both Cassini and Webb images. The organic sand absorbs more light than the water ice bedrock beneath it. The chemistry of this sand is one of the most intriguing unknowns on Titan. Scientists believe the organic particles falling from the haze are complex molecules that contain nitrogen, carbon, and hydrogen in combinations that are rarely found together on Earth. Some researchers have compared the surface chemistry of Titan's sand to the chemistry of very early Earth, before life began. The building blocks of biology, scattered across an alien desert. The sand does not just sit still. Seasonal wind shifts move material from one region to another. After a northern summer storm deposits methane rain somewhere distant, drainage patterns can shift and carry organic sediment into new locations. The dunes of Belet are not frozen in time. They are a living record of Titan's atmospheric chemistry, written in organic sand across thousands of miles. And just to the north of Belet, the surface changes again, rising into a bright plateau that looks almost impossibly out of place. Right next to the dark organic dune fields of Belet sits a region that glows. In the Webb infrared images, it stands out immediately. A wide, bright area sitting near Titan's equator, reflecting infrared light far more strongly than the surrounding dark sand. This is Adiri, one of the most prominent surface features on all of Titan, and the clearest example of what makes this moon so different from every other world in the solar system. Adiri is a highland region. Scientists believe it is built primarily from water ice bedrock, elevated above the surrounding terrain. On any other world, bedrock made of water ice would seem impossible. Ice is something you put in a drink. It melts at room temperature. It is fragile, temporary. On Titan, water ice is the most durable material on the surface. The temperature there is negative 290 degrees Fahrenheit. At that temperature, water ice does not melt. It does not flow. It does not erode the way rock erodes on Earth. It sits solid and rigid, harder than the concrete sidewalk outside your school. The entire floor of Titan is essentially a planet made of ice rock. Water ice reflects infrared light at the specific wavelengths that Webb's near-infrared camera uses to image Titan's surface. This is why Adiri glows brightly in the images, while the organic sand fields around it appear dark. The ice bounces infrared back toward the telescope strongly, while the dark organic material absorbs it. Adiri sits elevated above the dune plains, which suggests it is resistant to the wind erosion that reshapes the lower terrain. The organic sand blown by Titan's winds piles up in the lower areas but cannot easily climb the slopes of the higher icy ground. The boundary between the dark dunes of Belet and the bright surface of Adiri is one of the sharpest terrain contrasts on the entire moon. What is happening at that boundary is actually a window into Titan's geological history. Where rivers of liquid methane drain off the high ice terrain and flow into the lower dune fields, they carry organic sediment with them. The rivers carve channels into the ice bedrock, depositing dark organic material at their mouths where they meet the sandy plains below. Cassini captured several of these drainage systems in its radar mapping of the region. The ice bedrock of Adiri and regions like it across Titan holds another secret. Deep cracks and fissures in the ice might allow liquid from below to occasionally push upward. Some scientists believe that the ice crust of Titan is not fully solid all the way down. Beneath it, far below the surface, something liquid might be waiting. But that is a story for much later. What matters here is that Adiri is a geological marker. It tells scientists that Titan's surface has real topography, real highlands and lowlands shaped over billions of years, with chemistry and erosion working the landscape in ways that parallel Earth's geology, but with completely alien materials. The surface of Titan is not flat, it is not uniform, and it is hiding scars that should not exist. Every rocky body in the solar system gets hit. Asteroids, comets, and chunks of debris have been raining down on moons and planets for 4.5 billion years. The moon's surface is covered in craters. Mars is pockmarked. Mercury looks like it has been through a bombardment that never stopped. Titan should look the same. It has been sitting in the outer solar system for the same 4.5 billion years. The same debris field that scarred every other moon should have left its marks on Titan. But Titan's surface has almost no craters. The Cassini spacecraft spent years mapping Titan with radar, building up coverage of roughly half the moon's surface. In all that mapping, scientists found fewer than 100 confirmed impact craters. Compare that to a similar-sized body without an atmosphere, and you would expect thousands. This is not a mystery without answers. Scientists have identified several processes working together to erase Titan's crater record. The first eraser is the atmosphere itself. Titan's thick blanket of nitrogen and methane acts as a shield. Smaller space rocks that would punch clean through a thin atmosphere and crater the surface of an airless moon get slowed down dramatically by Titan's dense air. The friction heats them up and breaks them apart before they reach the ground. Only the largest impactors survive the journey through 400 miles of thick atmosphere to leave a mark on the surface below. The second eraser is liquid erosion. The methane rivers flowing across Titan's surface carve channels and move material constantly. Any impact crater sitting near a drainage system gets eroded over time. The sharp rim smooths. The interior fills with sediment washed in by rivers. Given enough time, a crater can become unrecognizable. The third eraser is the dune system. The organic sand blown across Belet and similar regions buries features under meters of dark material. Ancient craters in the equatorial zone could be sitting completely buried under dunes that formed after the impacts. The combination of these three processes means Titan's surface is constantly being refreshed. Old features get erased, new ones form. The surface geology visible today is relatively young compared to the underlying ice bedrock. But here is the deeper implication. If craters are being erased this rapidly, Titan's surface is geologically active on a timescale that surprised scientists. The methane cycle alone, moving liquid from seas to clouds to rain to rivers, reshapes the terrain continuously. Add in the organic sand transport and the atmospheric shielding, and you have a world that keeps overwriting its own history. Earth does the same thing. Plate tectonics, erosion, and volcanism erase old craters on Earth constantly. Titan has no plate tectonics, but it manages to accomplish similar results through an entirely different set of processes. A world that destroys its own craters is a world that is still changing. And if something has been fueling that change for 4.5 billion years, the source of that energy is hiding somewhere beneath the surface. Titan has rivers, real rivers, carved into the surface by flowing liquid, cutting through bedrock, building deltas, and draining into seas. This is one of the most remarkable confirmed facts about any world other than Earth in the entire solar system. And these rivers flow with liquid methane through canyons cut into solid water ice. Cassini's radar mapping caught river channels across many regions of Titan's surface. The most striking example is Vid Flumina, a river system draining into Ligeia Mare in the northern polar region. Vid Flumina is a branching network of channels that feeds into the sea, the same way the Mississippi River and its tributaries drain into the Gulf of Mexico. The scale is comparable to some major river systems on Earth. The main channel of Vid Flumina stretches hundreds of miles. The drainage network covers a region about the size of the American Midwest. What makes Vid Flumina even more remarkable is the depth of its canyons. Cassini data revealed that the river has carved canyons nearly half a mile deep into the surrounding terrain. These are deep, steep-walled gorges cut into ice bedrock by the slow but relentless flow of liquid methane over an enormous span of time. Half a mile deep, through solid ice, that is roughly as deep as the Grand Canyon. The carving process works similarly to how rivers cut canyons on Earth, through a combination of hydraulic action and chemical dissolution. On Earth, water dissolves limestone and other rocks as it flows. On Titan, liquid methane dissolves certain organic compounds in the ice bedrock and carries them downstream, slowly eating away at the canyon walls over millions of years. The rivers are not always flowing. Titan's methane cycle means that liquid flow is seasonal and episodic. During wetter periods, the river channels fill and flow strongly. During drier seasons, the channels may sit mostly empty, waiting for the next methane rain event to recharge them. This on and off flow pattern is similar to flash flood systems in deserts on Earth, where rivers run full during heavy rain seasons and then go dry for months or years at a time. On Titan, the dry periods last years rather than months. When a major methane rain event occurs, the sudden rush of liquid through the dry channels carries enormous erosive power. A pulse of liquid methane pouring down a steep canyon can move large amounts of organic sediment and deepen the canyon floor rapidly during each flooding event. The rivers deliver this organic material to the seas. The coastlines of Titan's seas are shaped by river deltas, where the sediment accumulates. Over millions of years, these deltas build up and change the shape of the shoreline. Everything about the rivers on Titan speaks to a world that has been geologically active for a very long time, shaping itself with the only tool available, a slow, cold cycle of methane raining from alien skies and carving ancient canyons through ice as hard as stone. What carved the first channels, though, and what keeps supplying the methane needed to run the whole system, was a question the Webb data could only partly answer. The real source might be buried far below anything a telescope can see. Stand on the surface of Titan, and you would feel the air pressing down on you more heavily than Earth's atmosphere does at sea level. The atmospheric pressure on Titan's surface is about 1.5 times the pressure you feel standing outside right now. It is as if you were standing at the bottom of a swimming pool, with an extra half pool of water above you. That extra pressure comes from the sheer mass of nitrogen packed into Titan's atmosphere. The nitrogen column above every square foot of Titan's surface weighs more than the nitrogen column above every square foot of Earth's surface, even though Earth's gravity is stronger. This happens because Titan has more total nitrogen in its atmosphere relative to its size. Earth lost much of its original atmospheric nitrogen through geological and biological processes over billions of years. Titan's colder temperatures and lower gravity allowed it to hold onto a thicker nitrogen blanket. The implications of this thick atmosphere affect everything on Titan. For sound, The thick atmosphere would make Titan unusually noisy. Sound travels better through denser air. A sound on Titan would propagate farther and carry more energy than the same sound on Earth. The wind, even though it is slow near the surface, would feel substantial, not because of its speed, but because the dense air pushing against anything in its path exerts real physical force. For light, the thick haze-laden atmosphere filters out almost all direct sunlight. The surface of Titan receives about 1,000 times less sunlight than Earth does. The light that reaches the ground after filtering through the haze would look dim and orange, similar to the light you see on Earth about 10 minutes after the sun drops below the horizon. A permanent deep dusk. For survival, a human without a pressure suit on Titan would not face the vacuum risk of being on the moon. The pressure would be survivable without a pressure suit. The problem would be the cold, negative 290 degrees Fahrenheit, which would kill instantly, and the atmosphere itself, which contains no oxygen, a simple oxygen mask, and extremely well-insulated cold weather gear would technically be the minimum equipment. That and some kind of jetpack, because the gravity is so low and the air is so thick that a person with large artificial wings could actually fly by flapping their arms. That is a confirmed physics result. Scientists at Cornell University ran the numbers. The combination of low gravity and high atmospheric density on Titan means that human flight is theoretically possible, with wings generating roughly the same lift as a large bird. You could, in principle, strap on wings and fly yourself across the methane dunes. For spacecraft, the thick atmosphere is both a challenge and an advantage. Breaking into Titan's atmosphere is easier than breaking into Mars's thin air. Heat shields work more effectively in thicker air. A parachute opened in Titan's atmosphere slows a falling spacecraft far more efficiently than on Mars. This is one reason the Dragonfly mission, a rotorcraft designed to fly through Titan's atmosphere, is feasible. The thick air gives rotor blades something real to push against. A helicopter on Mars needs enormous rotors spinning extremely fast just to lift. On Titan, the thick air makes flight almost easy. The atmosphere that hid Titan from telescopes for centuries turns out to be one of the moon's greatest engineering advantages for future exploration. But beneath all that thick air, the ground holds a mystery that the atmosphere alone cannot explain. Rain on Earth hits hard. Stand outside in a thunderstorm and the drops sting your skin. A heavy downpour can flood a street in minutes. The drops fall fast because Earth's gravity is strong and the atmosphere, while dense enough to slow things down slightly, does not offer much resistance to a falling water droplet. On Titan, rain is a completely different experience. Methane rain on Titan falls at roughly 1/5 the speed of rain on Earth. A droplet that would plummet to the ground in seconds on Earth takes much longer to drift down through Titan's thick air. The drops descend slowly, almost lazily, floating down through the orange haze like snowflakes falling through still winter air. Two forces combine to create this effect. The first is gravity. Titan's gravitational pull is about 1/7 of Earth's. Less gravity means less downward acceleration. A droplet released from a cloud on Titan simply does not get yanked toward the ground with the same urgency as a droplet on Earth. It falls, but gently. The second is atmospheric drag. Titan's atmosphere is 1.5 times denser than Earth's at the surface. Denser air creates more resistance against any falling object. A methane droplet pushing through that thick nitrogen atmosphere encounters significant drag that slows its descent further. Combine weak gravity with high atmospheric resistance, and you get rain that drifts. The size of the drops also matters. Scientists modeling Titan's methane rainfall found that individual drops would be substantially larger than Earth raindrops before they fall. Methane's surface tension is lower than water's, meaning methane droplets break apart into smaller pieces more easily. But in Titan's conditions, the slow fall and different air chemistry allow larger drops to survive the journey to the ground. Some models suggest Titan's methane raindrops could be several times larger than typical Earth raindrops, falling perhaps 10 times more slowly and reaching the ground with almost no impact force. A heavy rainstorm on Titan would look surreal from the surface. Huge, slow droplets drifting silently through orange murk, barely disturbing the surface of the methane sea or the organic sand when they land. No drumming on a roof, no rushing streams forming in minutes, just a slow, quiet accumulation of liquid building up across the landscape over hours. The rain does not fall often. Titan's weather cycle operates over long seasonal timescales. In some regions, a major methane rain event might occur only once every few Earth years. When it does happen, the sudden influx of liquid into dry river channels can cause flash flooding despite the gentle rainfall rate, because the channels have been empty for so long that even a modest accumulation moves quickly downhill. The Webb telescope confirmed that active cloud systems exist above Titan's surface right now. Those clouds are the source of methane rainfall. The slow, drifting rain from those clouds is the engine that keeps the rivers carving deeper into the ice canyons and keeps the methane seas topped up despite constant evaporation. But here is the problem that has haunted scientists for decades. The rain returns methane to the surface, but sunlight destroys methane in the upper atmosphere every day. Over millions of years, the destruction rate should have emptied Titan's methane supply completely. The math does not add up, and the answer to why Titan still has methane at all points somewhere deep underground. Titan should be dry by now. Sunlight hits the upper atmosphere of Titan continuously. When ultraviolet light strikes methane molecules, it breaks them apart. The hydrogen escapes into space. The carbon fragments recombine into heavier molecules and sink, building the orange haze and eventually settling onto the surface as organic sediment. This process destroys methane permanently. Once it breaks down into those heavier molecules and escapes as hydrogen, it is gone. The methane cycle can redistribute whatever methane exists on Titan, moving it between the atmosphere, the clouds, the rain, and the seas. But the cycle cannot create new methane. It can only move existing supplies around. The problem is the rate of destruction. Scientists calculate that sunlight destroys the methane in Titan's atmosphere over a timescale of roughly tens of millions of years. Titan is 4.5 billion years old. Over that span, sunlight should have broken down every molecule of methane on the moon many times over. And yet, Titan's atmosphere is still loaded with methane. About 5% of the atmosphere by volume is methane. The seas are full of it. It is raining from the clouds right now. Where is it coming from? The most widely accepted possibility involves the interior of Titan itself. Deep beneath the icy crust, the moon may contain pockets of primordial methane trapped in ice structures called clathrates. Clathrates are cage-like arrangements of water ice molecules that trap gas inside them. They form under high pressure and low temperature, exactly the conditions found deep inside Titan. If the interior of Titan contains vast reservoirs of methane locked inside clathrates, then geological activity could periodically break open those reservoirs and release fresh methane into the atmosphere. The release does not need to be dramatic or fast. A slow, steady seep of methane from the interior over billions of years would be enough to replenish what sunlight destroys. Another possibility, closely linked to this, involves cryovolcanoes. These are ice volcanoes that erupt not lava but a mixture of water, ammonia, and methane from deep within the moon. If cryovolcanoes are actively erupting on Titan, they could be pumping fresh methane into the atmosphere from below. Cassini searched for evidence of cryovolcanism on Titan during its 13-year mission. It found some intriguing surface features that looked like they could be volcanic in origin, low dome structures, and possible flow features. But the evidence remained inconclusive. No active eruption was ever directly confirmed. Webb's spectrograph data added another clue. The measurements of methane concentration in Titan's atmosphere were consistent with an ongoing source of new methane, but the data alone cannot identify where that source is. The mystery remains open. Titan is holding onto methane it should have lost billions of years ago. Something is feeding the supply. Something inside this moon is still active. And if Titan's interior is active enough to release methane, it might be doing something else entirely. Something that could change every assumption about where life can exist. Volcanoes on Earth erupt magma. Molten rock, superheated to over 1,000 degrees, pushed upward through cracks by pressure from below. The eruptions reshape landscapes, build mountains, and release gases that alter the atmosphere. On Titan, a volcano would look completely different. Cryovolcanoes, which translates roughly to cold volcanoes, erupt from the inside of icy moons. Instead of molten rock, they push out a slurry of water, ammonia, and methane from deep within the moon. The erupting material is still warm relative to the frozen surface, but it is cold by any Earth standard. The word volcano here describes the process. Pressurized material from the interior breaking through the crust, not the temperature. The idea that Titan might have cryovolcanoes comes from a combination of the methane mystery and some intriguing surface features spotted by Cassini's radar. Cassini imaged several regions of Titan that showed circular or dome-like structures inconsistent with impact craters or erosion patterns. Some of these features had raised rims and central depressions, similar to volcanic calderas on Earth. The region known as Sotrafacula showed a feature nearly 5 miles tall and a deep pit beside it, a profile that strongly resembles a volcanic structure. Flow features were also spotted nearby, regions where the surface appeared to have been covered by material that spread outward from a central point, the way lava flows spread from a vent on Earth. Cassini's instruments also detected unusual concentrations of certain chemical signatures in the atmosphere above these suspect regions, consistent with fresh material venting from below. The combination of the structural features and the atmospheric signatures made cryovolcanism one of the leading explanations for where Titan's methane originates. If cryovolcanoes are active, even intermittently, they could release bursts of methane into the atmosphere during eruption events, supplementing the slow seep from clathrate reservoirs. What makes this especially interesting is the heat source. For cryovolcanoes to work, Titan needs internal heat. That heat could come from tidal flexing. Saturn's enormous gravity constantly pulls and squeezes Titan as the moon orbits. This squeezing generates friction inside the moon's interior, which produces heat. Similar tidal heating is what powers the active volcanoes on Jupiter's moon Io and keeps the subsurface ocean of Europa liquid. If tidal heating is generating enough warmth inside Titan, the interior remains partially liquid, or at least warm enough to allow periodic eruptions through the ice crust. Webb's infrared instruments scanned Titan's surface, but were not specifically designed to detect heat signatures from potential volcanic vents. The cryovolcanism question remains one of the moon's most important unresolved problems. Direct evidence would require either a lander that could travel to one of the suspect regions and analyze the ground, or a long-term atmospheric monitoring mission that could detect the fresh chemical bursts that an eruption would produce. Dragonfly, the rotorcraft mission planned for the next decade, might be able to approach some of these regions from the air and sample the atmosphere directly above them. But until something lands and looks closely, Titan's possible volcanoes remain hidden under the ice, fueling a moon that should have gone cold billions of years ago. And if the interior is warm enough for cryovolcanoes, it opens a far more startling possibility. Beneath the dunes, beneath the ice canyons, beneath the methane seas, and beneath the frozen crust itself, scientists believe Titan is hiding an ocean, a liquid water ocean, global in scale, buried under miles of ice. This is one of the most significant and least discussed facts about Titan. The evidence is strong enough that many researchers consider a subsurface ocean not a fringe theory, but a leading model. The evidence comes from multiple directions. The first clue came from Cassini's gravity measurements. As the spacecraft flew past Titan repeatedly over its 13-year mission, Scientists carefully tracked how Titan's gravity field changed. A moon with a completely solid interior would have a uniform gravity field, but Titan's gravity field showed tidal variations. Slight changes in the gravitational pull depending on how Saturn was positioned relative to the moon. The size of these tidal variations was too large to be explained by a completely solid interior. The data matched what you would expect from a moon with a liquid layer somewhere inside, a layer that could flex and shift in response to Saturn's tidal pull. The ocean does not need to be near the surface. It could sit at depths of dozens of miles below the ice crust. The second clue came from measurements of Titan's rotation. Cassini found that Titan's solid outer crust rotated at a slightly different rate than the deep interior over time. This decoupling between the outer shell and the inner core is very difficult to explain unless a liquid layer separates them, allowing the two parts to slide against each other slowly. A subsurface ocean of liquid water mixed with ammonia fits both observations. Ammonia acts as antifreeze, lowering the freezing point of water significantly, allowing the ocean to stay liquid, even at the extreme cold temperatures inside Titan. The depth of this ocean is uncertain. Some models place it between 30 and 60 miles below the surface. Others suggest it could be shallower in some regions. The temperature of the ocean is also uncertain. Tidal heating from Saturn's gravitational pull likely keeps the water liquid, but whether that heating is enough to warm the ocean to any temperature significantly above freezing remains unknown. What would the ocean contain? Water and ammonia are confirmed likely components. Some researchers speculate that the organic compounds produced in Titan's atmosphere and deposited on the surface might eventually work their way down through the ice crust and into the ocean over geological timescales. If organic molecules reach warm liquid water, the conditions for the chemistry that preceded life on Earth would be present. This is the thought that makes scientists lean forward when they talk about Titan's interior. The ocean is real enough in the data that it is part of the planning for future missions. If Titan has a liquid water ocean, reaching it someday, even just detecting signals from it remotely, would be among the most important achievements in the history of space exploration. But there is a critical catch. The surface and the ocean are separated by dozens of miles of solid ice, and what happens between them may determine whether any of this matters for life at all. The surface of Titan is covered in organic chemistry. The dunes of Bellet are built from complex carbon molecules. The river channels carry organic sediment to the seas. The atmosphere continuously deposits more organic material onto the ground. Titan's surface is the richest collection of prebiotic chemistry in the solar system outside of Earth. Beneath the surface, miles down, sits a liquid water ocean. Put those two facts together and the question feels obvious. Could the organic material on the surface somehow reach the water below? Could chemistry from the top of Titan and chemistry from the inside of Titan ever meet? Many scientists believe the answer is probably no, and the reason is the ice. The ice crust separating the surface from the subsurface ocean is estimated to be tens of miles thick. This is not a thin shell. It is a massive, solid barrier of water ice that has been frozen solid for billions of years. For organic molecules on the surface to reach the ocean, they would need to pass through this entire layer. On Earth, surface material reaches the deep ocean through geological processes like plate tectonics, volcanic activity, and hydrothermal circulation. Plates subduct, carrying surface rock down into the mantle. Hydrothermal vents cycle water and chemistry between the deep ocean and the crust. Titan has no confirmed plate tectonics. The crust does not appear to be cycling material inward in any systematic way. Without a mechanism to pull surface material down through tens of miles of ice, the organic compounds sitting on top of Titan may be permanently isolated from the liquid water below. Cryovolcanoes provide the most plausible exception. If an eruption punches through the ice crust, it could potentially bring subsurface water up toward the surface, but that would move material upward, bringing ocean water toward the top, not pushing surface organics downward. Some researchers have proposed that large asteroid impacts could temporarily melt part of the ice crust and create a transient crater lake, where surface organics and ocean water mix briefly. The impact would punch through some of the ice. The heat would melt the rest temporarily, and for a period of perhaps thousands of years, a warm, chemically rich liquid lake would exist on the surface before refreezing. This scenario has been modeled mathematically. The results suggest it is physically possible. Whether it has actually happened on Titan depends on the size of impactors that have reached the surface and whether the ice crust was thin enough in those locations. The irony of Titan is deep. It has the most complex surface organic chemistry of any world scientists know of. It has a liquid water ocean inside, but the two may be permanently separated by a wall of ice too thick for chemistry to cross. Life, if it exists on Titan, would therefore exist in two completely isolated environments. Surface life, if possible at all, would need to survive in the methane seas using chemistry entirely unlike anything on Earth. Subsurface life, if present in the ocean, would have developed in warm water with no contact with the rich organic chemistry above. Two separate experiments in life, running in parallel, on the same moon, and the question of whether either experiment succeeded is one that no telescope, including Webb, can currently answer. Webb did not just take pictures of Titan, it read it. The near-infrared spectrograph aboard Webb is one of the most sensitive instruments ever built for this purpose. It takes incoming light from a target and splits it into thousands of individual wavelengths, like spreading white light through a prism into every color of the rainbow. Every chemical element and molecule absorbs and emits light at specific wavelengths, leaving a unique fingerprint in the spectrum. By reading those fingerprints, scientists can identify exactly what a target is made of without touching it. When Webb's spectrograph analyzed the light from Titan's lower atmosphere, it found chemical signatures consistent with complex carbon-based molecules forming right now, in the present, actively being assembled in the air above the moon's surface. The process works like this. Sunlight hits methane in the upper atmosphere and breaks it into fragments. Those fragments react with nitrogen to form simple compounds like hydrogen cyanide. These simple compounds then react with each other and with more methane fragments to build longer and more complex molecules. The chains grow heavier and longer over time, eventually forming the large organic particles that sink to build the haze layers. Webb's spectrograph caught evidence of this chain-building process happening in the lower atmosphere at altitudes closer to the surface than previous instruments had probed. The chemical signatures identified were consistent with nitrile compounds, molecules built from chains of carbon and nitrogen atoms bonded together. These types of molecules are considered building blocks for more complex chemistry, including, in the right conditions, the kinds of molecules associated with life. This does not mean life exists in Titan's atmosphere. The temperature is far too cold, and the chemistry is happening in a methane-nitrogen environment very different from anything biology uses on Earth. But the fact that complex carbon chains are actively assembling themselves in Titan's air right now is scientifically extraordinary. Earth's early atmosphere, roughly 4 billion years ago, before life began, was rich in similar nitrogen-carbon chemistry. Some researchers believe that a version of this chemistry, driven by lightning and ultraviolet light in the early atmosphere, eventually produced the first biological molecules. The process on Titan is a cold, slow version of what may have happened in Earth's early skies. Titan's atmosphere is essentially running a chemistry experiment that Earth ran 4 billion years ago, at a fraction of the speed, preserved in cold storage, observable today. The spectrograph data also revealed detailed information about the altitude structure of the haze. Different types of organic molecules are concentrated at different heights, forming distinct chemical layers stacked above the surface. The lowest layers, closest to the surface, contain the heaviest and most complex molecules. Higher up, the molecules are simpler and lighter. This layering reflects the history of the chemistry. Complex molecules take time to build. They start simple in the upper atmosphere and grow heavier as they sink and age, accumulating complexity through billions of years of continuous chemical reactions in the skies of Titan. The atmosphere above us is doing nothing like this. Titan's sky is a factory, and the product of that factory is raining down onto the surface below every single day. 4 billion years ago, Earth looked nothing like it does today. There were no forests, no oceans teeming with fish, no oxygen in the air. The early atmosphere was thick with nitrogen, methane, and carbon dioxide. Ultraviolet light from the young sun bombarded the surface constantly. Lightning cracked through dense clouds of ammonia and water vapor. In that environment, chemistry was running wild. Simple molecules were colliding, breaking apart, and reassembling into increasingly complex structures. Chains of carbon atoms were growing longer. Nitrogen was bonding into new configurations. The building blocks of biology were forming in the atmosphere and raining down into the warm oceans below. This period in Earth's history is sometimes called the prebiotic era, the time before life, when the chemistry that would eventually become life was still assembling itself. Titan's orange haze is made from the same class of molecules that dominated Earth's prebiotic atmosphere. Scientists call these complex organic materials tholins, a word coined in the 1970s to describe the reddish-brown organic gunk that forms when you expose mixtures of nitrogen and methane to ultraviolet radiation in a laboratory. Tholins are not a single molecule. They are an enormously varied mixture of organic compounds, chains of carbon, hydrogen, and nitrogen bonded together in countless different arrangements. When researchers have produced tholins in laboratory experiments designed to mimic Titan's atmospheric chemistry, they have found something striking. The tholins contain amino acid precursors, molecules that are one chemical step away from becoming amino acids. Amino acids are the building blocks of proteins, which are among the most fundamental components of life on Earth. Titan's haze is continuously producing these precursor molecules and raining them down onto the surface below. The dunes of Bellet, the river sediments, the coastal deposits around the methane seas, all of it is coated in this complex organic material that shares a chemical heritage with the early Earth. The comparison is not just poetic, it is chemically specific. Several experiments have taken samples of synthesized titangent-like tholins and hydrated them, meaning they mixed them with liquid water, then analyzed the results. The hydrated tholins produced simple biological molecules spontaneously. Uracil, one of the nucleobases found in RNA, has been identified in these experiments. Glycine, the simplest amino acid, appeared as well. This means that if Titan's surface organics ever came into contact with liquid water, the chemistry would likely generate molecules directly relevant to the origin of life, automatically, without any special conditions required. There are 2 places on Titan where surface organics could contact liquid water. The first is through cryovolcanic eruptions, where water from the interior briefly reaches the surface. The second is through large impact events that melt the ice crust temporarily. Both scenarios are considered possible. Neither has been confirmed as currently active. What is confirmed is that Titan's surface is loaded with the most complex prebiotic chemistry found anywhere outside Earth, and it has been accumulating for billions of years. The experiment has been running for a long time. Whether it produced a result is the question that no current instrument can answer. This one sounds like science fiction. It is not. If you stood on the surface of Titan and strapped on a pair of large artificial wings, you could flap them and take flight. Real, sustained, powered flight. The kind of flying that requires nothing more than your own muscle strength and the right wing design. This has been calculated by actual physicists. The math checks out. Flight depends on lift. Lift is generated when a wing moves through air fast enough to create lower pressure above the wing than below it. The faster the wing moves, or the denser the air, the more lift is generated. On Earth, birds fly because their wings are shaped and sized to generate enough lift in Earth's air at speeds their muscles can sustain. Titan's environment shifts that equation in a radical direction. First, the atmosphere. Titan's air at the surface is 1.5 times denser than Earth's sea-level air. Dense air produces more lift per square foot of wing surface per unit of speed than thin air. A wing that generates modest lift on Earth generates significantly more lift in Titan's thicker atmosphere. Second, the gravity. Titan's gravitational pull is about 1/7 of Earth's. That means your body weight on Titan would be roughly 1/7 of your Earth weight. If you weigh 150 pounds on Earth, you would weigh about 21 pounds on Titan. Combine those two factors. You weigh 1/7 as much. The air provides 1.5 times the lift. The ratio of lift available to weight that needs to be lifted is dramatically more favorable on Titan than on Earth. Researchers at Cornell and other institutions have run the specific numbers. A human with wings spanning roughly 8 to 10 feet, shaped similarly to bird wings and operated by normal human arm and chest muscles, could generate enough lift on Titan to achieve sustained flight. The muscle power required would be within the range of a physically fit person. You would need to breathe, which means bringing your own oxygen supply, since Titan's air is nitrogen with no breathable oxygen. You would need extreme cold weather protection, since the temperature is -290 degrees Fahrenheit. But the flight itself, mechanically, would work. This is not just a thought experiment for imagining future tourists flapping over Titan's methane dunes. It has real implications for mission design. If a human-scale mass can be made to fly through Titan's atmosphere using relatively modest power, then robotic aircraft on Titan can be made far more efficient than robotic aircraft on Mars. Mars has a thin atmosphere where flight is extremely difficult and energy-intensive. Titan's thick air makes aerial vehicles natural fits for long-range exploration. The Dragonfly mission exploits this directly. Dragonfly is a rotorcraft roughly the size of a large car, designed to fly through Titan's atmosphere using rotors. The same atmospheric density that would let a person fly with artificial wings makes Dragonfly's rotors efficient enough to lift the spacecraft repeatedly across the surface, covering more ground than any rover could in a fraction of the time. Flight on Titan is easy, almost surprisingly easy. What the aircraft sent to fly there will find on the surface is the harder question. On January 14th, 2005, a small probe named Huygens became the first spacecraft to land on a world in the outer solar system. It survived 72 minutes. Huygens was built by the European Space Agency and had been riding along with the Cassini spacecraft since its launch in 1997. After Cassini arrived at Saturn in 2004 and began orbiting the planet, it released Huygens on a trajectory aimed directly at Titan. The probe drifted toward the Moon for 3 weeks before hitting the atmosphere. Entry into Titan's atmosphere happened at roughly 13,000 miles per hour. The heat shield on Huygens glowed from the friction of plowing through the dense air at that speed. For the first few minutes, the probe was a fireball falling through an alien sky. Then the parachutes deployed. First, a smaller drogue chute to stabilize the probe. Then a larger main chute to slow the descent. Huygens floated down through Titan's atmosphere for over 2 hours, taking measurements and transmitting data back to Cassini overhead the entire time. The descent itself was scientifically extraordinary. Huygens measured the temperature, pressure, and chemical composition of the atmosphere at every altitude from entry all the way to the ground. It recorded wind speeds and directions. Its cameras captured images of the landscape below as it descended, showing what looked unmistakably like a drainage system. Dark channels cutting through bright terrain, flowing toward a darker lowland region. Then Huygens touched down. The landing site was a flat plain covered in rounded pebbles. Scientists describe them as looking like river rocks, smooth and rounded by the action of flowing liquid over long periods. The pebbles were made of water ice, worn smooth by ancient methane rivers that had since gone dry. The surface material around the pebbles appeared soft and slightly spongy, described by scientists as similar to wet sand or lightly packed snow. The probe sank slightly into it on impact. The air temperature at the surface was -290 degrees Fahrenheit. The atmospheric pressure was 1.5 times Earth's. The sky, from the camera images, glowed dim orange. Huygens transmitted data from the surface for 72 minutes before its battery drained, and it went silent permanently. In those 72 minutes, it told scientists more about Titan's surface conditions than any instrument had collected in the previous 300 years. It also captured the sound of Titan. Huygens carried a microphone. The audio recordings captured the hiss of wind and the faint creak of the probe's own structure settling on the alien surface. It was the first audio ever recorded on a world beyond the inner solar system. 72 minutes, then silence. The probe still sits on that flat plain of ice pebbles somewhere in Titan's dimly lit landscape, frozen solid, buried perhaps under years of slowly drifting organic snowfall, waiting for the next visitor to arrive. And that visitor is already being built. When the Huygens probe landed on Titan and its cameras began sending back images, scientists gathered around screens at mission control and stared at something completely new. Not space, not craters, not the barren rocks of Mars or the airless grey of the moon. A landscape. The images showed a flat, grey-orange plain stretching to a hazy horizon. Scattered across the surface were rounded objects of different sizes, from pebbles a few inches wide to rocks the size of a football, all of them smoothed and worn, all of them made of water ice, polished by the flow of ancient methane rivers until their sharp edges were gone. The horizon was close. Titan's thick haze limited visibility to about a third of a mile. Beyond that, the atmosphere swallowed everything in a dim orange murk. The sky above was a dull amber, filtering the distant sunlight down to a glow roughly equivalent to the light on Earth just after the sun drops below the horizon. The ground between the rocks appeared soft and dark. Instruments on Huygens confirmed that the surface material was a mixture of organic particles and fine ice grains, compressed slightly by the probe's landing. The probe's penetrometer, a spike designed to measure surface hardness, recorded a soft impact followed by firmer resistance below, consistent with a thin layer of loose material sitting on top of harder ice bedrock. What the images did not show was liquid. The landing site was dry. The river channels captured during the descent had clearly been formed by flowing methane at some point, but the surface at landing was not wet. The methane had drained away or evaporated long before Huygens arrived. The descent images, taken from altitude during the parachute drop, were arguably even more dramatic than the surface shots. From several miles up, Huygens photographed a network of dark channels branching and converging across the landscape below. The channels were clearly drainage systems, narrow tributaries joining into wider rivers, all flowing toward lower terrain. The pattern was indistinguishable from a river drainage system on Earth when seen from altitude. Scientists used those descent images to map the drainage patterns and estimate flow rates from ancient methane floods. The scale of the carved channels suggested powerful, sustained flows over long periods, consistent with a moon that experienced heavy methane rainfall during past seasonal cycles. The combination of the landing images and the descent images built the clearest picture yet of Titan as a geologically active world shaped by fluid processes. Not hypothetically, visually confirmed. Huygens also recorded a drop in methane humidity close to the surface, suggesting that the ground was slowly evaporating trace amounts of liquid methane even at that dry landing site. The surface was not completely dry at the molecular level, just visually dry. Those 72 minutes of data remain the only ground truth measurements ever collected from Titan's surface. Every climate model, every atmospheric simulation, every surface chemistry prediction built since 2005 has been calibrated against what Huygens saw and measured in that short window. The images showed a world that looked surprisingly familiar in structure, if completely alien in chemistry and cold. And in those same images, visible even from altitude, was the dim, permanent twilight of a place where the sun barely matters. The sun is about 886 million miles from Titan. At that distance, sunlight is already much weaker than what Earth receives. Earth sits roughly 93 million miles from the Sunday. Titan is nearly 10 times farther away. Because light intensity drops with the square of the distance, Titan receives about 1/100th of the solar energy that Earth gets per square foot of surface. That would already make Titan dim, but the orange haze above the surface takes what little sunlight arrives and filters it further. The haze layers in Titan's atmosphere scatter and absorb incoming light at visible wavelengths. Much of the sunlight entering the top of the atmosphere never reaches the surface. By the time the remaining light filters down through hundreds of miles of nitrogen and organic smog, it arrives at the surface as a dim, warm-toned glow that scientists estimate is equivalent to roughly 1,000 times dimmer than a clear sunny day on Earth. For a sense of what that looks like, stand outside on Earth just after the sun drops below the horizon on a clear evening. That residual glow, when the sky is still lit but the direct sunlight is gone, is roughly the brightness of a midday on Titan. It looks like dusk, permanent, unchanging dusk. Every single day, for a Titan day that lasts about 16 Earth days, the light level stays in that same permanent twilight range. The color adds to the strangeness. The orange haze filters the incoming light strongly toward the red and orange end of the spectrum. The blue wavelengths are scattered out before they reach the surface. So the light that arrives at ground level is not just dim, it is orange and warm-toned, like late afternoon sunlight passing through thick wildfire smoke. Standing on Titan's surface, you would see no blue sky, no white clouds, no direct disk of the sun in the sky, just a uniformly glowing orange dome above you, slightly brighter in the direction of the sun but with no sharp edge or defined solar disk visible. The haze diffuses everything. Saturn itself would not be easily visible from the surface either. The haze is too thick for the naked eye to pick out the planet, though radar and sensors could detect it. Standing next to one of Titan's methane seas, you would see the dark liquid surface stretching away to a hazy orange horizon, the rounded ice pebbles of the shoreline, the dim organic dunes in the distance, all bathed in the same unvarying amber twilight. The Huygens probe's descent cameras captured this light environment directly. The images show the same orange-amber tones visible throughout the descent from atmospheric entry to the surface. This permanent dim orange light is actually one reason why the Webb telescope's infrared capabilities were so valuable. Infrared light behaves differently from visible light in Titan's atmosphere. By using infrared wavelengths, Webb could effectively see past the haze that makes visible light almost useless for surface imaging. But while telescopes need infrared to see through the haze, the Dragonfly rotorcraft flying inside the atmosphere will operate in that amber twilight directly, navigating a world where the sun is always setting and never quite arrives. Right now, engineers at Johns Hopkins University Applied Physics Laboratory are designing a rotorcraft that will one day fly through the same orange atmosphere. Webb photographed in November 2022. Every piece of data Webb collected about Titan's clouds, wind patterns, atmospheric density, and surface chemistry is feeding directly into the planning of that mission. The mission is called Dragonfly. NASA approved it as part of its New Frontiers program. It is a dual quadrotor rotorcraft, meaning it carries 8 rotors arranged in 4 pairs, similar in concept to a large consumer drone but built for an alien world. It weighs roughly 1,000 pounds and carries a full suite of scientific instruments, including cameras, mass spectrometers to analyze surface chemistry, seismometers to detect interior activity, and atmospheric sensors. The plan for Dragonfly is unlike any mission flown before. Previous landers and rovers have stayed close to where they touched down. Mars rovers cover maybe a mile or 2 during their entire operational life. Dragonfly will fly, taking advantage of Titan's thick atmosphere and low gravity. Dragonfly will hop across the surface in a series of flights, each one covering several miles before landing to take samples and measurements. Over its planned operational lifetime, Dragonfly is expected to cover more than 100 miles of total distance across Titan's surface, visiting multiple sites, including the organic dune fields and the potential cryovolcanic regions. The Webb observations are critical for this planning process in several specific ways. The cloud data helps engineers model the weather windows Dragonfly can safely fly through. If cloud systems build and move rapidly, as the Webb and Keck data showed, flight planning needs to account for changing atmospheric conditions. Understanding the seasonal and regional patterns of cloud activity tells mission planners when and where flying is safest. The atmospheric density and composition data from Webb's spectrograph helps engineers design the rotor systems with precision. Rotor efficiency depends on the exact density and viscosity of the air being pushed. Small errors in atmospheric modeling lead to large errors in rotor design. Webb's measurements provided an updated baseline for the current state of Titan's atmosphere. The surface mapping from Webb's infrared images helps identify landing targets. Dragonfly needs landing sites that are relatively flat and free of large obstacles. The infrared maps showing the contrast between the dune fields, the icy highlands, and the coastal regions near the methane seas help narrow down safe approach and landing zones. One of Dragonfly's primary science targets is the region called Selk Crater, an impact crater where a large asteroid strike in the ancient past melted the ice crust and briefly mixed water and organic surface material. Scientists believe the chemistry that occurred in the temporary liquid lake at Selk could be preserved in the crater sediments today. Dragonfly is designed to fly there and sample those sediments directly. The launch window for Dragonfly is currently planned for around 2028. After launch, it would take several years to reach Saturn's system. It would arrive at Titan in the early 2030s. When it lands, it will be carrying the accumulated knowledge of every telescope, spacecraft, and Earth-based instrument that has ever looked at Titan, including the first infrared images Webb captured in 2022. The real answers are still years away, but the questions Webb raised are the questions Dragonfly will go to answer. The moment Dragonfly arrives at Titan, the mission timeline unfolds in a sequence carefully designed to squeeze every possible discovery out of each flight and landing. The rotorcraft enters Titan's atmosphere using a heat shield and parachute system similar to the one that delivered Huygens in 2005. Once safely through the atmospheric entry phase, the rotors spin up and Dragonfly begins powered flight. The first landing site is in the dune fields of the Shangri-La region, near Titan's equator. This region is covered in the dark organic sand dunes built from complex carbon molecules falling from the atmosphere. By landing here first, the mission team gets an early chance to measure the chemistry of Titan's surface organics directly. Dragonfly carries a drill that can sample the top layer of the dune material and feed it into the onboard mass spectrometer. The spectrometer heats the sample and analyzes the gases released, identifying the exact molecules present. This will be the first direct chemical analysis of the organic compounds covering Titan's surface, turning spectral inferences from telescopes like Webb into concrete molecular data. From the dune fields, Dragonfly hops progressively toward higher priority science targets. Each flight covers several miles, with the rotorcraft cruising at an altitude of a few thousand feet above the surface before descending to the next landing zone. The target that most excites scientists is Selk Crater. This impact crater is estimated to be about 5 miles in diameter and was formed when a large asteroid hit Titan roughly 1 billion years ago. The impact was energetic enough to melt the ice crust within the crater and create a temporary lake of liquid water mixed with the surface organic material. That transient warm water lake may have lasted for hundreds to thousands of years before the cold refroze everything. During that window, the organic chemistry on the surface was dissolved into warm water, and the reactions that followed could have produced molecules far more complex than anything achievable through dry chemistry alone. Dragonfly will land inside Selk Crater and sample the sediments that have been sitting there since the lake froze. If the prebiotic chemistry that occurred in the temporary water lake produced identifiable biological building blocks, the mass spectrometer on Dragonfly will find them. Beyond Selk, mission planners have identified potential targets near suspected cryovolcanic regions. If Dragonfly can sample material near an active or recently active vent, it would be collecting the freshest possible material from Titan's interior, giving scientists their first direct look at what the subsurface chemistry is doing. The entire mission is designed around flight as a tool for exploration. Rovers are limited by terrain. A rotorcraft hops over canyons, dunes, and rough ice terrain that would stop a wheeled vehicle completely. The 100+ miles of coverage planned for Dragonfly would take a Mars-style rover decades to accomplish. Dragonfly is expected to operate for at least 2.5 Earth years on Titan, running on a radioisotope power system that generates electricity from the decay of nuclear material, the same power source used by Cassini and the Voyager probes. 2.5 years on Titan, flying across methane dunes, landing in ancient craters, sampling the chemistry of a world that may hold clues to how life began. The data from those flights will be the most detailed portrait of Titan ever assembled. And at the center of every measurement Dragonfly takes will be the most important question ever asked about this moon. Every telescope, every spacecraft, every dataset collected about Titan points to the same unanswerable question. Could something be living in those methane seas right now? It sounds absurd at first. The seas are a mixture of methane and ethane at -290 degrees Fahrenheit. No life on Earth could survive in those conditions for a single second. Every organism biologists have ever studied requires liquid water to function. The chemistry of life on Earth runs on water as its solvent. Take the water away and replace it with liquid methane, and everything breaks down. But that assumption, that life requires water, is based entirely on the one example of life we know, Earth life. Some researchers at Cornell University have proposed a theoretical biochemistry that could function in liquid methane. They call the hypothetical life form an azotosome, built from nitrogen-hydrogen-carbon molecules instead of the phospholipid membranes that contain Earth cells. These molecules could theoretically form stable membranes in liquid methane at Titan temperatures, creating cell-like structures that could hold chemistry together in the methane seas. This is speculative. There is no direct evidence that azotosomes exist or that methane-based biochemistry is possible in practice. But the theoretical case for it is chemically sound enough that serious researchers have published papers on it in peer-reviewed journals. What would observational evidence of methane-based life look like? Scientists have suggested a few possible signatures. Hydrogen gas in Titan's atmosphere. Sunlight and cosmic rays produce hydrogen continuously by breaking methane apart. If something in the methane seas was consuming hydrogen for energy, the concentration of hydrogen near the surface would be lower than predicted by purely chemical models. Cassini detected a depletion of hydrogen near Titan's surface consistent with this idea. But the depletion could also have a non-biological explanation. Acetylene on the surface. Acetylene falls from Titan's atmosphere and should accumulate on the surface. If methane-based life forms were using acetylene as a food source, surface concentrations would be lower than expected. Cassini found less acetylene on the surface than models predicted. Both anomalies are intriguing. Neither is conclusive. Both have possible non-biological explanations involving standard chemistry. Webb's observations were not designed to detect life signatures. The telescope measured cloud systems, atmospheric chemistry, and surface features. It was not equipped to detect the subtle chemical depletion patterns that would hint at biological activity. Dragonfly, flying directly through the atmosphere and landing on the surface, will have a chance to measure surface chemistry at a level of detail that could clarify both anomalies. If the hydrogen depletion and acetylene depletion are real and local, Dragonfly might detect them directly. Whether the answer turns out to be biology or chemistry, the question itself has fundamentally changed how scientists think about the boundaries of life. Life might not require water. It might not require warmth. It might not look like anything evolution has ever produced on Earth. And Titan is the closest place we have to test that idea. Every time scientists study Titan, they find something that rewrites the assumed rules for where life can begin. Before Titan was studied closely, the standard model for habitable worlds was simple. You needed liquid water on the surface. You needed the right temperature range. You needed a rocky planet in the zone around a star where water stays liquid. Everything else was too cold, too hot, or too chemically wrong. Titan has broken nearly every part of that model. Start with liquid on the surface. Titan has it. The substance is not water, it is methane and ethane. But the structure is identical. Stable bodies of liquid covering large areas of the surface, connected by river systems, driven by an active weather cycle. The framework of a hydrological world exists here, even though the chemistry is completely alien. Move to organic chemistry. The basic building blocks of life on Earth are carbon-based molecules assembled from simple precursors. Titan's surface is covered in the most complex collection of carbon-based molecules found anywhere outside Earth. The atmosphere produces them continuously. They have been accumulating on the surface for billions of years. The raw materials for an origin of life chemistry event are available in quantities that dwarf anything present on any other world scientists know. Consider subsurface liquid water. If the theoretical ocean buried beneath Titan's ice crust is real, and the evidence suggests it probably is, then Titan has liquid water too. It is not on the surface where sunlight could drive chemistry directly, but it exists, potentially warm enough to sustain reactions and deep enough to be shielded from the harsh radiation environment above. Think about energy sources. Life on Earth uses sunlight and chemical gradients as energy sources. Titan has both potentially available. Sunlight, even dim and filtered, reaches the surface. Chemical gradients between the oxidized surface organics and the reduced methane atmosphere exist, and if cryovolcanism is active, fresh chemical energy from the interior is occasionally delivered to the surface. The implication is that Titan is not a borderline case for habitability. It is a world that passes every single habitability test, except the one test that assumes Earth-like conditions as the standard. It fails only if you define life as requiring what Earth life specifically requires. If you define life more broadly, as any self-replicating chemical system capable of using available energy and chemistry to maintain organization, then Titan is one of the most promising habitable environments in the solar system. This matters far beyond Titan. The galaxy contains hundreds of billions of planets and moons. Most of them are cold. Most of them are not in the narrow habitable zone around their stars, where surface liquid water is possible. If life can start in cold methane chemistry or in subsurface oceans beneath ice, then the fraction of potentially inhabited worlds in the galaxy expands from a small number to something potentially enormous. Titan is a proof of concept argument for a universe that is far more full of life than Earth-centric biology would suggest. Whether life actually exists on Titan or not, the Moon has already done its most important work. It showed us where to look. Saturn has 83 known moons. Jupiter has almost 100. The solar system is full of moons, ranging from tiny, irregular rocks a few miles across to large, complex worlds with their own geological and atmospheric stories. None of them are Titan. Titan is the only moon with a dense atmosphere. It is the only world beyond Earth with stable liquid on its surface. It contains the most complex prebiotic organic chemistry of any world scientists have ever studied. It likely hides a global subsurface ocean of liquid water. Its atmosphere is actively manufacturing the same class of molecules that preceded life on Earth, and it has been doing all of this for 4.5 billion years. The James Webb Space Telescope turned its infrared eyes toward Titan for the first time in November 2022 and delivered images that changed the conversation. The two methane clouds confirmed active weather. The surface maps confirmed geological diversity. The spectral data confirmed ongoing organic chemistry in the lower atmosphere. And the combination of Webb and Keck data showed that Titan's weather evolves faster than expected. with cloud systems reorganizing visibly in under 48 hours. Every observation adds weight to the same conclusion. Titan is not a cold, dead moon at the edge of the solar system. It is an active, complex, chemically rich world that operates on its own rules. The exploration of Titan is still in its early stages. Huygens landed for 72 minutes. Cassini mapped the surface with radar from orbit. Webb captured the first clear infrared images of the clouds and surface together. Each step has revealed something new and opened 3 more questions that need answering. Dragonfly will push the exploration forward in ways no previous mission could, flying across the surface, sampling the organic dunes, landing in ancient craters where water and organics briefly mixed, and potentially sampling material near cryovolcanic vents. The rotorcraft will collect more direct data about Titan's surface chemistry in its first year than all previous missions combined. But Dragonfly still will not reach the subsurface ocean. It will not sample the methane seas directly. It will not give a definitive answer to whether anything lives in the liquid methane or the buried water below. Those questions are waiting for missions that have not been designed yet. The science coming back from Webb showed something important beyond the specific data about clouds and atmospheric chemistry. It showed that Titan is complex enough and dynamic enough to justify a long-term, sustained commitment from space agencies. Webb sees Titan from 1 million miles away and still finds new surprises. From the surface, the discoveries would be overwhelming. Titan is the most complete natural laboratory for prebiotic chemistry anywhere within reach of human spacecraft. It holds answers to questions about the origin of life, the boundaries of habitability, and the potential abundance of life elsewhere in the galaxy that no other location in the solar system can provide. The orange moon of Saturn has been hiding its secrets for 370 years, since the moment Christian Huygens first spotted it through his handmade telescope. Webb cracked the door open. It is time to walk through it.